Hello, we're Project 22. I'm Vishnu and my partner is Andy, and this is our mid-year progress update. This is the data capture system that we designed. It's just 3 RealSense cameras mounted onto an aluminium rail. This is a great improvement from the pole that we had last time because there's no way that these cameras will move while moving down the track. As for why we chose this particular configuration, it's because we wanted to have multiple angles of the fruit or region that we're scanning as we go down the track. We found that one snapshot per 25 centimeters gave us this result. The alignment of the cameras is commonly called an endpoint perspective problem. We hold out a checkerboard the camera can calculate the pose of relative to itself. Then, since we know the checkerboard pose should be the same across all cameras, we find it and apply a transformation matrix, which we found using the equation below. We used an existing library in ROS named TUW checkerboard to find the checkerboard pose, then crafted the rest of the solution in ROS ourselves. After aligning the cameras, I took some test data on very small fruits. 9 point clouds were overlapped to reconstruct the model shown at the bottom left. I noticed how small errors and distortion across the point clouds greatly reduced the quality. Ultimately, we want users to recognize clusters of fruits, so I looked further into refining alignment. The image at the bottom right shows the model reconstructed only using the middle camera. There is visibly less depth distortion and fraying due to a more consistent frame across snapshots. As for how we could improve the reconstruction, I came up with 2 performance metrics. Firstly, how well does a point cloud represent the world? And secondly, how good is the alignment between point clouds? To test the world representation, I held out a measuring tape and compared projected and real distance. In general, distance perception in the horizontal and vertical axis was pretty great, but depth perception was pretty bad, up to 10% at 1 meters. We used RMSE between point clouds as a performance metric. We had around 2 centimeters RMSE between the bottom and top cameras. For perfectly aligned point clouds, the RMSE was around 5 millimeters just due to naturally occurring error. You may ask, why not just take RMSE as an objective function to minimize? ICP already does this, and iteratively tries to minimize the RMSE. We used the Open3D implementation to trial on our data, and quickly found that ICP has heavy limitations. Mainly where it worked, it did not necessarily mean a visually improved point cloud. As seen on the right, the fruits are overlapping, and it would be hard for a person to see which fruit belonged to what cluster. Thus, we didn't use ICP in our final implementation. Ultimately, only using the middle camera for visualization resulted in the best looking point cloud. The top and bottom camera will still be used for detection and matching. We also designed an approach to match the detected fruits across cameras. Here is the method, and here is the results. All 7 fruits in the real world were detected, with the color box showing which camera first detected it.